application engineer. Before we present EZtol, I will do a short presentation about Ariadne. We are a consulting company that focuses on simulation. We help our customers to build products with higher quality faster using simulation at an early stage. We have 3 areas. First is software, and we work in every software we sell. CAD is usually done in Creo, but because we are connected to a PTC partner. But as we are consultants, we work in all CAD softwares on the market. We also promote GD&T Laser, and that is a Formolag GPS wizard for Creo. When it comes to tolerance analysis, we use EZtol 6 Sigma, which is a 3D tolerance tool. It's directly integrated in Creo, SolidWorks, CATIA, and NX. So if you're looking at variation analysis in 3D, this is the tool to use. Today we're looking at EZtol, which is a 1D tolerance analysis software from Sigmetrics. When it comes to consulting, we do everything from basic FEM analysis to tolerance analysis, and also optimization projects. Our expert field is on Formolag, GPS, and variation analysis. Training, we have developed our own Formolag GPS training, which has proven very successful. So this is a training we do for a big number of companies, both in Sweden and abroad. We have a global concept on this area. We have training that learns designer how to use FEM in CAD in a simple, effective way. And we also offer a innovation training called Trees, which is like a structured brainstorm session. When it comes to Sigmetrics, we are a certified Nordic competence center. That means that we can do everything regarding Sigmetrics products, training, implementation, and we also do consulting. We're going to look at EZtol today, and a lot of people who do tolerance analysis today use spreadsheets. So this is a comparison. So the 5 main points: spreadsheets is not connected to the CAD file. You have to create a report manually with spreadsheets. There is no warning or indication that it might be a rotational effect to 2 or 3D in spreadsheets. No statistical approach, only worst case and RSS. And it's very hard to visualize, and in spreadsheets will make sharing and discussions around the analysis very difficult. So that's from me, and I'll hand you over to Felix for the demo. Just gonna make him a presenter. There you go, Felix.
All right, my name is Felix, and I'm gonna give a short technical demo on EZtol. It's gonna be about 20 minutes, and after that we can have a Q&A session if you have any questions. So this is EZtol. It's a standalone application which can import files from different CAD systems. So it's based on the Inventor package. So obviously it supports Autodesk Inventor, but we can also open files from CATIA, NX, Creo, SolidWorks, or some of the standard files like STEP or Aegis. In this case, I'm going to open a SolidWorks assembly. And we have 2 main options, which is we can either reference the model, which creates a link to the original CAD file. And whenever you update that CAD model, it will also update the EZtol file. Or we can convert the model, which creates a separate Inventor file to store the EZtol information inside. And that's what I'm going to do in this case, since it's a bit faster. So we're importing our CAD model into EZtol. And then we have the EZtol interface here. So on the left is the familiar CAD tree. In the middle, we have our model. On the right is where we're going to have our tolerance stack up. And we also find the settings here. And the settings, we can configure our default tolerances for linear and size dimensions and for geometric tolerances. We can set our first analysis type, but this is just the default one, and we have access to all for every stack-up. We can set the value for our statistical quality metrics, the capability of our input dimensions, and the annotation size. Up here, we have the EZtol commands and some view commands, like changing visual style or creating section views. So for this demo, we're going to use the caster wheel here, which you can find on shopping carts or hospital beds, for example. And size is how coaxial these two bushings are. So for that, I'm just going to make the wheel and the axle invisible. So we're going to analyze the coaxiality of this hole towards this one. For that, we choose a new stack up. And then we have this little prompt menu, which guides you through the stack up process. So I select the features. Then I select the direction, since the coaxiality could be measured in vertical, horizontal, or at any angle. In this case, I'm going to choose vertical, and then I'm going to place my dimension. In the next step, we would like to choose the components of which the tolerance stack-up consists. So we already have the bushing on the left. After that, we would like to choose the axis support, the top plate, and then down on the other side. In the last step of creating our tolerance stack-up, we can choose the faces which connects the different components of the model. And then we click OK. And that's it. We have our stack up here. We can see the dimension on the left and here on the right as well. So these are our stack up details. We have the components here, for example, bushing 1, axis support 1, and then the features which are important for our tolerance stack up. So our stack up starts with the hole here, and then it goes to the shaft because that's where it connects to the axis support. For each feature, we have our tolerance here. This is the default tolerance we chose at the beginning. We can change from symmetric to one-sided tolerances or choose limits. And in between the features, we have the dimension which connects them. In this case, since they are both size features, they have the same axis, so the dimension in between is 0. For those kind of features, we can also choose geometric tolerances here. And then we have the feature controlled on top, which is always the above feature, and then the datum down here. To make it a bit easier, we can choose to name the shaft datum A, and then choose our geometric tolerance, and then it looks a bit more familiar. Since they are both size features, we can choose from position tolerance, total runout, circular runout, and coaxiality. For position tolerance, we support material modifiers both on the target and the datum. So even if I don't really know how a geometric tolerance affects my tolerance stackup, I can just input it like it's on the drawing, and EZtol will calculate that automatically for me. So we have our geometric tolerance here on one side. Just go down here, also select it on the other side. And since on this side the datum A is the incoming feature, we can swap it around here, so we have it as our datum. What you see here is the optimal dimensioning scheme. So it's the shortest possible tolerance chain, which has the lowest amount of variation. If it looks a bit differently on the drawing, we can add some features. For example, if those two surfaces of the top plate are toleranced with a profile tolerance towards the top of the top plate, we can add it through the Add Feature button, and then it will appear here in our tolerance stackup. Then I can just create the tolerance between them. If I name this again as my datum A for the top plate, it looks a bit better. Then I can just add the profile tolerance for one surface and for the other. When I put in after I put in all my tolerances, I get the result down here. This is my stackup 1. I can change the name to vertical coaxiality. And make it a bit bigger. So down here we have the objective. The default objective for every stackup is equal or greater than 0, because most of the analysis we deal with are interference analysis to see if we have a sufficient gap between parts. Again, I can change it here: lower limit, upper limits, general limits, one-sided tolerances, objectives, or symmetric. For this one, I'll put in symmetric and put my objective to 0.5. As default, we have first the worst case analysis. So in this case, in the worst case, I'm outside my limits to support root sum square, which is also common in spreadsheet-based stackups. Besides that, we can choose from 4 different statistical methods. So we can CPK, sigma, percentage of yield, or defective parts per million opportunities. So in this case, I will choose CPK. And we have our normal distribution down here, our actual CPK, our mean, and standard deviation. So if my target is 1.6, I can see the limits of the CPK 1.6 distribution would be 0.475, which is well inside my objective limits. So my actual CPK is 1.7. If I would like to have a CPK of 2, maybe, I can see I'm not within a CPK of 2, because those limits would be 0.583. Besides that, it will give you a small message down here. that calculated results are ignoring potentially significant 3D effects. So this means that this analysis is not solely one-dimensional, and the calculated variation is probably lower than the actual one. Additionally to that, I will get a list of the contributors, sorted from the highest to the lowest. Usually for an assembly, we don't only have one stack up, but multiple. So I'll quickly create another one to show you how it looks that way. In this case, I will analyze the total height of my caster wheel. So I'll go from the top to the wheel. I'll put my dimension here. I select the components. And again, I have my stack up. I can see immediately that some of the tolerance already filled out. So these are the ones I used also in my previous tolerance stack up. So whenever EZtol sees I'm reusing a tolerance, it will automatically put that in. I will also get this little message here, which says that a certain tolerance is used in more than one stack up. So I know whenever I'm going to change this tolerance, it will affect the other stack ups as well. So we can see here, our measurement only goes to the midpoint of the wheel. We can change that down here. We can either have go to the near, to the center, or to the far. And then again, I can put in my objective and the analysis type down here. Here we have our summary with the nominals, objectives, the targets, results, and the predicted quality, and the summary screen down here. We also have the contributors for all stack ups combined. So we can see which dimension contributes the most to the overall function of this model. Then one last part, the report creation. We have an automatic report function where we can, through generating the report up here, first we can take some pictures for the report. So when I'm here at the summary stage, I can click the snapshot up here, and that will be the main picture for my report. Then I can also go into each individual stack up and have a picture of that one. Then I can generate the report up here. Give it a name, and it will create an HTML document, which we can open in our favorite web browser. So here's the main picture for our report of our model. Then down here, we have a summary of our stack-ups, and then a detailed view of each stack-up with the tolerances, their sensitivities, nominal values, and tolerance types. The distribution I chose, and the contributors. So this is a very fast way of generating the reports where you have visual information which you can share with your colleagues. So that's it so far from me. I guess we can take questions now. Daniel?
Yeah, I'm just gonna finish up with a last slide. So let's see. Here we go. So thank you everybody for joining the demo, joining our webcast. If you want to have a closer look at EZtol, just contact me. We do workshops, we do training, and if you're interested in seeing a demo with your colleagues and you have some challenges you want to have a look at, we can set it up, no problem. We have some coming trainings and demos. We have a webcast introduction to Formula GPS on the 22nd of March. We also have a webcast EZtol, Six Sigma, the 3D tolerance tool on the 5th of April. And then we have some trainings. The Formula training, GPS training, 3 days in April, the 11th, and the FEM for designers, 3 days on the 28th of May. So that's everything for us. If you have some questions, I'm gonna